In this lesson we're going to be looking at three different types of force fields that are on your Leaving Cert Physics course, and what we're going to do is, I suppose, compare the three and see the similarities between them, and also look at some of the differences. So one by one, the first field we're going to look at is the gravitational force field, and this is always caused by one or more masses. And you can see what it might look like here. If we could see this invisible force field, you might see lines, we'll say in the example of the apple and the earth, lines going from the apple down towards the earth here. And the second field we're going to look at is the electric field, and electric fields are always caused by static charges. And again, this is what it might look like if you could see the field. If you saw, for example, a plus charge and a minus charge here, you would see field lines coming out curved in this fashion here. And the easiest way to think of these field lines, I think, is to imagine, I always try to imagine, it's like parachuting in a plus charge. If you parachuted in a plus charge, it would be repelled by the plus charge here and would be pushed along this line and pulled towards a minus. So that's how you can always determine the direction of the field lines. And the last one I want to look at is the magnetic field. And the magnetic field is caused by north-south poles in magnetic materials, or also by moving charges. So we see, again, very similar to the electric field, I suppose, here, the field between a north and a south pole, but caused by different phenomena. Now we're going to look at some of the simulations to compare these three fields. And first we have a simulation here of gravity. So if I run this, there we have the example of the Earth rotating around the Sun, and the blue arrow indicates the direction of the force due to the gravitational field. So you can see there's an equal and opposite force on the Sun and on the Earth, and this force is given by Newton's universal law of gravitation. So that's a gravitational field. We want to move on to the next one. We're now going to look at a simulation of an electric field. We have one here. So the first thing I'm going to do is take out a plus charge. And you can see, again, if we could see this invisible field, that's what it might look like. You'd see these arrows going out from the plus charge in all directions. And again, as I said earlier, the way to think of this is if you parachuted in a plus charge, that's the direction the plus charge would travel in along those arrows. It would be pushed away by the existing plus charge. And we can bring a minus charge into this, and you can see how the field changes as a result. Now again, if you keep this visual image in your head of parachuting in a plus charge, if I parachute in a plus charge, somewhere in the middle there, it's going to be pulled towards the minus because its opposites attract, and it's going to be pushed away from the plus. So it's pushed from the plus towards the minus along those arrows there. The other thing we can do is we can test the electric field strength at different points. And we've got an instrument here that can do this for us. It's an electric field sensor. Just get this working here now. So there it is. So this electric field sensor, in your physics course, you've got Coulomb's law, which gives you the force between two charges, like these two charges here, which is a very useful law. But the trouble with having the force between two charges is it tells you nothing about the force due to just one charge on its own. And that's what this here does. The idea of this electric field sensor, as we call it, is it's the equivalent of putting in a 1 Coulomb charge. Maybe take away this minus for a minute, keep things simple. So it's the equivalent of putting in a 1 Coulomb charge and measuring the force between the plus and the 1 Coulomb charge here. And when you do that, we instead of calling it the force between the two charges, we now call it the electric field strength at this point here. So this is just emphasizing the difference between the force between two charges and the electric field strength at a point due to a charge. So the electric field strength at the point where this sensor is, this 1 Coulomb charge, which is a sensor basically, the force at that point where it is, due to this plus charge in here, is given in this case by 4.9 volts per meter. Okay, so that's an electric field, and the big difference, of course, as well between electric fields and gravitational fields is gravity always attracts. Two masses always attract, whereas two charges can attract or repel. You know, if you put in two plus charges there, they're pushing each other apart. Again, think of what would happen to a plus charge parachuted in the middle there. He'd be pushed from the left and pushed from the right. You know, there's thus the direction of the arrows. Okay, and we're on to the last type of field, which is, of course, a magnetic field. We've got a simulation of that here. So there's a bar magnet, and the field lines, again, if you could isolate a north pole, I mean north and south always occur in pairs, but if you can imagine a north pole isolated, and if you put a north pole just, I mean the compass basically represents the north pole. If you put your north pole anywhere in the diagram here, you see that the compass shows that the field lines are the direction of the force field again. So you'll find that, for example, if you can imagine this as a north pole, it would always be attracted to the south, to the opposite of the magnet. So that's the red arrow here. So think of this red as basically an isolated north pole, and you can see that it's pointing towards the south all the time. It's attracted towards the south. So when you move this plotting compass around, it basically gives you the direction of the magnetic field. And again, we can show this thing called a field meter, and the field meter corresponds to the magnetic flux intensity, which is on your physics course, because what that's measuring is again the strength of the field at a particular point. So it's the equivalent of the electric field strength in the electric field. So electric field strength, which we call E normally in the electric field, the equivalent is B in a magnetic field. And its magnetic field intensity, as I said, measures the strength at different points. And again, as you'd expect, just like in a charge, the closer you get, the stronger the effect is. And the further out you go, the weaker it gets. So that there it is, magnetic flux intensity B. And that's the end of the lesson on the three fields. So just once more to summarize, we looked at the three different fields: gravitational field, which is an attractive force only between two masses; electric field, which can be attractive or repulsive, between two charges. Well, it's caused by one or more charges, but we took the example of two charges. And lastly, a magnetic field, which can be attractive or repulsive as well. So you can have north pole attracts south, and north pole repels north, south repels south, etc. Okay, so that's the end of this lesson for today.